Howdy, chemistry fans! We are going after day 64 here, where we dig into some more work with Stoich and solutions, and also look at a thing called Beer's Law. Today, you will hopefully understand how Beer's Law works and how you can use it to find the concentration of an unknown solution. And in class, you would feel a bit of your inner Dr. Evil, yes. Now, if we look at this, you'd normally grab two papers, but good news from my mini-me. Your solutions test is going to be the next week during your COVID vacation. That, of course, will be week number 4, where you'll get a bit more about Stoich and solutions, and then you'll get a remote assessment that you'll be turning in to see how well you understand this. I'm looking forward to it. If we look at our ETD today, you're going to write it down. It's ETD 64. Consider the following reaction. Make sure you think about what's going on in that thing and what's missing from it. And then you're given some facts. See if you can solve it. So this will be a good time, of course, to pause the video and get rid of my big ugly head. And try it out in your ETD and see what you know, right? So pause me, and then we'll come back in a millisecond and solve it together. And here we go. If we look at this, the first thing I do is I see a reaction, so I stick it on a teeter-totter and ask myself, hey, is it balanced? No, it's not. You can see that you have 2 sodiums going in, so you need 2 sodiums coming out. You can also notice that these are aqueous solutions, and I got a little double switcheroo. This is an aqueous too, but that makes a new solid because that stuff's still not going away, right? Takes 2 insolubles, make a solution turn white, and barium sulfate is white. Now, when I'm looking at the question itself, one thing I can see is there's some gots and some needs. And what I need here is I need the volume of that solution. And if I need a volume, of course, I'm going to measure that in liters. So that's the end of this, and it's going to be a solution of that sodium sulfate stuff. But I want to know how much of that 0.15 I'm going to be actually producing, right? And that tells I got some stuff. I got to produce exactly 57 grams of my product, my solid, my barium sulfate. So, as in most chemistry, if I want to get to the end, I can work backwards. I want to get the liters. I know that I got 57 grams of the barium sulfate. I'm starting there because I want to work my way to the other thing that contains the sulfate. I also have that 0.15, and that'll come in handy in just a second, right? Now, key things with this, I'm going to use the power of dimensional analysis. I got 2 different substances and I got 2 different units. So first hand is if you see a G thing, turn the G thing into a mole thing, right? So I'm going to get rid of the grams of the barium sulfate. I'm going to turn it into piles of barium sulfate, the old mole trick, right? 1 pile, that's pretty darn heavy. It's 233.40 grams, right? That will get rid of the grams and put me in moles. And once I'm in moles of my product, I can get back to the loveliest thing I want, which is my reactant. So I'm going to use the old moles to mole ratio trick. I'm going to get rid of barium sulfate in my product and work my way backwards to my reactant, which was the sodium sulfate that it's asking about. When I do that, I can see that there's 1 to 1 of those, which is good. It's a 1-to-1 ratio, making it conversion easy. Next step. I've gotten rid of the barium sulfate. Now I'm in the right substance, but I'm in totally the wrong unit. I want to get the liters. So if I want to get the liters, that means that liters has to be on top of the sodium sulfate. And here's the great thing that I know. I know that in every 1 liter of this sodium sulfate reaction, there are 0.15 moles of sodium sulfate because it's a 0.15 molar solution of that stuff. So what I did here is pretty simple. I took the moles per liter and I did the old flip trick. And by doing that, I can have liters over moles. I can still use the conversion factor, just like we could go from miles per hour and turn it into hours per mile. You can do the old flip trick, which is handy if it's ever asking for a volume, because you just need to make sure you cancel your units correctly. Moles and moles disappears, liters is on the top, and it's the right substance, so I set it up correctly, right? Now, that means that I would multiply, divide, multiply, divide, multiply, divide, and get my product coming out the other end. When I do that, you should get about 2 Siggy Figgies. That's going to be 1.6 liters of the sodium sulfate. That, of course, is of the sodium sulfate solution, because that's what I was starting with. Now, before I move on, I should ask myself if that number makes sense. Well, I wanted to get 57 grams of barium sulfate, which is a fairly large amount, even though it's pretty heavy, right? That's about a quarter of a pile of that stuff. And if I think about what I started off with a solution of sodium sulfate, and that sodium sulfate was 0.15 molar, right? So that means that it's got a tiny little smidgen of a pile of that stuff, not a full pile, right? Just a smidgen of that pile. And that's pretty low concentration. So if I had 1 liter of that, that could be a decent amount of it, which means that I'd need another, 0.6, almost half a liter more to get a bit more of a smidgen of that 0.5 to add up to actually equal to 57 grams of barium sulfate. So it's a quarter of a pile of that, so I'm going to need a few piles of the sulfates to get my way there. So the number does make sense. You're going to need like a liter and a half-ish of that stuff. Cool. Now, normally we'll be going over Stoich and solutions, which is the questions that are mainly on your sheet for this week. If we look at then when we go after this thing called Beer's Law. And Beer's Law is fairly straightforward. Kids like it because it's the story of light beer versus dark beer. And if we look at Beer's Law really is looking at the fact that if I look through a light beer, I can see through it because it's fairly transparent. That's because there's not a lot of stuff in the solution of light beer. That's why it's less filling and better for your health, so to speak, if you're drinking the lighter beers, because there's less sugars that are inside of that. Dark beers are thicker and more filling because they've got more stuff in them. And the more stuff in them does a better job of absorbing the light because it's more concentrated. The darker the beer, the more stuff that's in the solution, the more that it blocks or absorbs light as it goes through it. So the lighter the solution, the less concentrated. The darker the solution, the more concentrated. And Beer's Law works really, really well with solutions that have color. And not all solutions have color. It won't work very well for clear solutions, at least with visible light, but it will work for things like infrared light. Now, key things we should notice, that means in this lab you would get to work with lasers, like Dr. Evil. And of course, we could have some sharks with lasers on their heads, but, the sharks are in danger, so we just have to deal with the lasers. When we use those lasers, it's good to recognize that the light that's coming from these lasers is visible light. And visible light, of course, comes in all the colors of the rainbow, and there's a trick to it. The shortest wavelengths we can see are the violet ones, right? And then Roy G. Biv, you go the other way, the longest wavelengths we can see are the red ones. And then, yellow and orange are in the middle. Roy G. Biv, going that way. If I look at Dr. Evil's shirt, there's a trick to this. What color is his lovely business suit here? Well, a lot of people would say it's blue, but actually his coat here is any color but blue. It absorbs all the wavelengths except for blue. Blue is reflected. Now, a laser, of course, is just in one wavelength of light if it's a good laser, and this is a red laser, so, of course, that red laser would be absorbed by his blue coat. If it was a blue laser, it would be completely reflected by his coat. So keep in mind that the color of your shirt is the color it is not. It's the color that it reflects. It absorbs the other colors. So a white background reflects all the colors. A black background absorbs all of them, right? So looking into that, of course, that means you have to be careful about what color laser you use. If you've got a green solution, then you would not want to use a green laser because it wouldn't absorb any of it, right? So here's the part you should write down. Beer's Law is all about this thing called absorbance versus concentration. How much it absorbs and soaks up versus how much stuff's in the solution. So absorbance is the amount of light that a sample can absorb. Kind of makes sense. And then if we look at that, we measure it with a thing called a colorimeter. It can measure the colors coming through it. It's a color meter. Very creative. What's the relationship between concentration and absorbance? Well, it's pretty straightforward. The higher the concentration, the darker the beer, the more it absorbs the light. That's why it's darker. In addition to that, the lower the concentration, the less it absorbs the light, the more passes through. That's called transmittance. The lower the absorbance. So what you would have is you'd have this colorimeter, and inside of it there's a light bulb that produces a laser. And that laser would shoot through a sample in a tiny little thing called a cuvette, which of course is a little tiny test tube with your sample in it. So if I was shooting my laser through this blue sample and I used a blue laser, it would all reflect off, and of course none of that stuff would be absorbed. It measures how much light travels through it on the other side. So probably if I was using a blue sample of a solution, like a cupric chloride solution, I would use a red laser because I know that that red would be absorbed by the blue solution because it's absorbing everything but the blue. And then the amount of light that passes through would tell me how much got absorbed by the sample. But you'd have to compare it to a standard. That would be your control group, which would be pure water because it would be completely transparent and let all the visible light through it at this level, right? So to measure that, of course, you'd adjust it, and that sample you'd want to use a red laser because it's blue. Well, it's every color but blue because it reflects it. Oh, it's so tricky. Now, other things that we should write down. What is Beer's Law? Well, Beer's Law can be derived, and you would have derived it in your lab, by this. It looks at the absorbance, the A's, compared to the concentration. And you can see that they are arranged over each other because, well, if one goes up, the other goes up. It's a direct relationship. Absorbance is basically how hard it is for light to get through the solution. The more concentrated it is, the more particles there are per liter, so therefore it's harder to get through it. Kind of makes sense. So if one goes up, the other goes up. It's a direct relationship. Great thing about this is you can just think about it in terms of the Beer's law. It's named after scientist Beers, but beer will help you with that. Dark beer, more stuff, more absorbance, more concentrated. Light beer, less stuff, less concentrated. So the cool thing is the more particles you have, the less light gets through. Kind of makes sense if you think about dark clouds and all that stuff. And then you can see a sample here. I got a 1 mole per liter and I got a 2 mole per liter. Hey, it's twice as concentrated and it's twice as dark. It absorbs twice as much light. So if you were to then go into the lab and shoot with your little cuvettes, it'd be kind of fun. You'd have to add in the sound effects because lasers are silent. Sorry, Star Wars. And as you do that, of course, you would derive a graph that looks like this. The graph would be a nice direct relationship with a predictable slope of like 1 with the samples that we use. And you'd have a series of standards that would give you that thing. And when you did that, of course, the lowest absorbance would be for the pure water because it's going to pass through. And then as it gets darker, because you do a serial dilution at each step, that serial dilution would allow you to derive this direct relationship. Now, cool thing about this, each of these is a standard. This one is a higher concentration. Then we would dilute it down using the dilution formula to 1/10 of that concentration, and then 1/10 of standard 2 and 1/10 of standard 4, watering it down at each step in a series dilution. And then we'd shoot it with the laser, and that would tell us how much absorbance, because the computer is good for doing that. It tells you how much light gets absorbed. Now, the nice thing about this is if you get an unknown and you shoot it, and you don't know its concentration, you shoot it, you'd find out its absorbance with the computer. The laser would tell you how much got absorbed. Then you could follow across to, well, a point on the graph, follow down and go, hey, it's at that unknown concentration. This is typically how scientists today actually find the concentration of unknown substances and identify them as well, is by using lasers of different types, whether it's an infrared laser or a UV laser, or in this case, a visible light laser, which works for colored solutions. So the cool thing is you can stick the sample in once you have your standard curve to compare to, like most of science, and you can find out how concentrated it is just by shooting a laser, which makes it easy. Plus, lasers are fun. Now, speaking of lasers, we would normally end it today finishing off our Beer's Law lab. You get some claim reasoning evidence. That would be great. But because this is remote time, you've got that 5-question sheet with a bunch of other questions buried inside of it. And we got a baby elephant with a laser, because sharks are endangered. But so are baby elephants. Maybe they could defend themselves from poachers. And I digress. Now, cool things about this, of course, you hopefully understand Beer's Law. Beer's Law is just absorbance over concentration. As you increase the concentration, put more particles in solution, you're going to absorb more light. So it's a direct relationship. How do I use it to find the molarity of an unknown? Well, I would set up myself a nice standard curve doing a serial dilution. That would give me a curve or a nice straight line with a direct relationship. I'd shoot my unknown and it would tell me exactly what its concentration was using the absorbance. Hey, almost seems pretty easy. Cool. Next week, we will go more into Stoich solutions and look at things like limiting reactants. Oh, baby, I miss that stuff. All right. Hope you're doing well there, folks. Catch you later. Be careful playing with lasers.